In this video, we are going to look at how to linearize nonlinear ordinary differential equations. The goal is to approximate a nonlinear ODE by a linear ODE near an equilibrium point. The original nonlinear ODE is the full model. The linearized ODE is not a replacement for the full model everywhere. It is local, which means it is only intended to describe behavior close to the equilibrium point. This is useful because linear ODEs are easier to analyze, and they prepare the ground for linear control methods. Once we have a local linear ODE, we can study how small deviations from equilibrium behave over time. Let's start with a specific example of a nonlinear ODE, which we will use throughout this video. x double dot plus cx dot plus k sine x equals u. Here, x is the system variable, and it depends on time. The input u may also depend on time. The parameters c and k are constants describing the system. The nonlinear part is the sign dependence on x. In other words, the equation is nonlinear because x appears inside sine x. Our goal is to approximate this nonlinear ODE near an equilibrium point so that we can study small deviations from that equilibrium. Before we linearize the equation, we need to choose an equilibrium point. At equilibrium, the system is not changing. So x dot equals 0 and x double dot equals 0. We write the equilibrium position as x sub e and the corresponding constant input as u sub e. Substituting these equilibrium values into the ODE gives k sine x sub e equals u sub e. This means that u sub e is the constant input needed to hold the system at the equilibrium position x sub e. For example, if x were an angle, u sub e could represent a constant torque that holds the system at a chosen angle. So, at equilibrium, the input u sub e balances the nonlinear term k sine x sub e. For this video, we do not need to find every possible equilibrium point. We choose one equilibrium point and linearize near that point. For now, we assume that one equilibrium pair has been chosen, x sub e and u sub e, satisfying u sub e equals k sine x sub e. Finding equilibrium points is an important step, but it is not the main focus of this video. We will treat finding equilibrium points as the topic for another video. Here, our focus is what happens near that equilibrium point. We define delta x of t as the deviation from the equilibrium position. So, delta x of t equals x of t minus x sub e. Or, equivalently, x of t equals x sub e plus delta x of t. Since x sub e is constant, the time derivative of delta x is the same as the time derivative of x. So, delta x dot of t equals x dot of t, and delta x double dot of t equals x double dot of t. This happens because shifting the equilibrium point only changes where we measure x from. It does not change how x is changing with time. In other words, it does not change the first or second time derivative. We also define delta u of t as the deviation from the equilibrium point. So, delta u of t equals u of t minus u sub e. Or, equivalently, u of t equals u sub e plus delta u of t. As a notation note, we are using uppercase delta x here to mean a small deviation from equilibrium. Some control texts use lowercase delta x for the same idea, but the meaning in both cases is simply the change away from the equilibrium value. To prepare for the linearization step, it is useful to write the ODE as a single expression equal to 0. We move everything to one side and then call the left-hand side f. So f of x, x dot, x double dot, and u equals x double dot plus cx dot plus k sine x minus u. At the equilibrium point, x equals x sub e, x dot equals 0, x double dot equals 0, and u equals u sub e. Therefore, f of x sub e 0, 0, u sub e equals 0. The next step is to approximate how f changes near this equilibrium point. To do that, we will use partial derivatives. We now use partial derivatives to linearize f near the equilibrium point. The idea is similar to the tangent line approximation for a function of one variable, where the derivative gives the slope of the local straight line approximation. Here, f depends on four quantities: x, x dot, x double dot, and u. So, instead of a single slope, we get one local slope for each of these quantities. Each slope is found using a partial derivative. For example, when we differentiate with respect to x, we hold x dot, x double dot, and u fixed. When we differentiate with respect to x dot, we hold x, x double dot, and u fixed. The same idea applies for x double dot and u. This means that during the calculation, we temporarily treat the current values of x, x dot, x double dot, and u as separate arguments of f. After the linearized equation is formed, delta x dot and delta x double dot still mean the time derivatives of delta x. Now we apply the partial derivative idea to our expression for f. First, we differentiate f with respect to x, while holding x dot, x double dot, and u fixed. The only part that depends on x is k sine x. So the partial derivative is k cos x. At the equilibrium point, this becomes k cos x sub e. Next, we differentiate with respect to x dot. The only part that depends on x dot is cx dot, so the partial derivative is c. With respect to x double dot, the partial derivative is 1. Finally, with respect to u, the partial derivative is -1, because the expression contains minus u. These four values are the local slopes that we will use to build the linearized equation. Now we use the local slopes from the previous slide to build the linear approximation for f. The approximation has one constant term, f sub e, plus one contribution from each deviation. The x contribution is k cos x sub e delta x. The x dot contribution is c delta x dot. The x double dot contribution is delta x double dot. And the input contribution is minus delta u. The constant term is fe, which means f evaluated at the equilibrium point. But at equilibrium, f of x sub e 0, 0, u sub e equals 0. So the constant term is 0 because the equilibrium point already satisfies the original ODE. Since the original ODE was written as f equals 0, the linear approximation for f is also set equals to 0. We can then move the input deviation back to the right-hand side to get the final local linear equation. We now have approximated the original nonlinear ODE by a local linear ODE. But it is important to interpret this correctly. The original equation describes the full nonlinear system. The linearized equation describes small deviations from the chosen equilibrium point. So, delta x is not the original position. It is the deviation from x sub e. And delta u is not the original input. It is the deviation from u sub e. This linearized equation is only intended to be valid near the equilibrium point, where the deviations are small. Also, notice that the coefficient k cos x sub e depends on the equilibrium point. So, if we choose a different equilibrium point, we may get a different local linear ODE. Another valid way to derive the same local linear equation is the substitution method. Instead of first defining the whole left-hand side as f, we substitute the deviation variables directly into the nonlinear ODE. We write x as x sub e plus delta x, and u as u sub e plus delta u. Since x sub e is constant, x dot becomes delta x dot, and x double dot becomes delta x double dot. Substituting these into the original ODE gives an equation in terms of the deviations. At this stage, the equation is still nonlinear because it still contains sine x sub e plus delta x. The next step is to linearize that remaining nonlinear term. This method is not a shortcut, and it is not less formal. It is another legitimate way to derive the same local linear model. However, when the nonlinear terms become more complicated, the partial derivative method is usually safer to use because it is more systematic and reduces the chance of missing terms. So, if you are unsure, use the partial derivative method. We now linearize the remaining nonlinear term. The nonlinear term is sine x sub e plus delta x. Using the tangent line approximation near x sub e, this is approximated by sine x sub e plus cos x sub e times delta x. Substituting this approximation into the equation gives the term k sine x sub e on the left-hand side and u sub e on the right-hand side. But from the equilibrium condition, u sub e equals k sine x sub e. So these constant equilibrium terms cancel. This leaves the same local linear equation we derived using the partial derivative method. So the substitution method and the partial derivative method are two ways of expressing the same local linear approximation. In our example, f depended on four quantities: x, x dot, x double dot, and u. But the same idea applies to more general nonlinear ODEs. More generally, we can write the ODE as one expression equal to 0 and call that expression f. F may depend on x, its time derivatives, the input u, and possibly derivatives of the input. In other systems, there might be several system variables, such as theta 1 and theta 2, or several input variables, such as u1 and u2. The linearization idea is the same as before. We take one local slope for each quantity using partial derivatives evaluated at the equilibrium point. Because the chosen equilibrium point satisfies the original ODE, the constant term is 0. So, the linearized equation describes how small deviations affect f near that equilibrium point. The substitution method also works more generally. We substitute the equilibrium values plus deviations into the equation, then approximate the nonlinear paths so that the final equation is linear in its deviations. For complicated expressions, this can become messy. The partial derivative method is usually the more systematic way to get the same local linear results. Let's finish by summarizing the linearization recipe. First, choose an equilibrium point. This gives the equilibrium values such as x sub e and u sub e. Second, write the ODE as one expression equal to 0. This gives us the expression f that we want to linearize. Third, Define deviation variables such as delta x and delta u to describe deviations away from the equilibrium point. Fourth, compute the partial derivatives at the equilibrium point. These give the local slopes used in the linear approximation. Finally, build the local linear ODE for the deviation dynamics. As we saw, there is also another valid approach after defining the deviation variables. Instead of using steps 4 and 5, we can substitute the deviation variables first, then linearize the nonlinear terms directly. But when the equation becomes more complicated, the partial derivative method is usually safer to use because it is more systematic and reduces the chance of missing terms. In both cases, the result is not a replacement for the full nonlinear model everywhere. It is a local approximation that describes behavior near the chosen equilibrium point.